I need to tell you about something absolutely wild that's happening right now with this interstellar comet. And honestly, I'm sitting here looking at the newest data from NASA, and I still can't quite believe what I'm seeing. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. So, NASA just dropped a fresh alert today about this comet called 3I Atlas. And the reason they put out this alert is because this thing is still active when it has absolutely no business being active anymore. Like, it should be winding down right now. It should be getting quieter, it should be fading into the background. But it's not doing any of that. It's doing the complete opposite. And that's why this is so fascinating and, frankly, a little bit unnerving. Let me back up for a second and explain what normally happens with comets, because understanding what's supposed to happen makes what's actually happening so much more interesting. When a typical comet swings past the sun, there's this really predictable pattern that plays out. The comet comes in from the outer solar system, it gets closer and closer to the sun, and as it does, the sun's heat starts cooking the ice and frozen materials on the surface. That heat makes those ices turn directly into gas without becoming liquid first, and that gas carries dust with it as it escapes. That's what creates the beautiful glowing cloud around the comet, what we call the coma, and the long tail streaming behind it. The closest point to the sun is called perihelion, and that's when things get really intense. That's peak activity time. The comet is getting hammered by solar radiation, it's heating up like crazy, and it's throwing off massive amounts of gas and dust. This is when comets look their most spectacular. But then, after perihelion, after the comet passes that closest point and starts heading back out into the cold depths of space, something very predictable is supposed to happen. The comet is supposed to calm down. The activity is supposed to drop off in this nice, smooth curve. Less heat means less gas, which means the coma starts to shrink, the tail starts to fade, and the whole show gradually winds down until the comet is just this dark, quiet little rock drifting back out into the darkness. That's the script. That's what's supposed to happen. That's what our models predict. And that's what we see with the vast majority of comets. 3I Atlas is not following that script. Not even close. This thing passed perihelion weeks ago. By now, based on how far it is from the sun, it should be noticeably dimmer. The brightness should be dropping off at a steady rate, the gas production should be falling, everything should be winding down. But when astronomers compared the brightness measurements from last week to what they're seeing today, something jumped out at them immediately. The comet hasn't dimmed the way it should have. I mean, yes, it's a tiny bit fainter than it was at its absolute peak, but the drop is way too small for how far away from the sun it is now. If you take the predicted light curve, the brightness curve that tells us how bright the comet should be at different distances from the sun, and you overlay it on top of the actual observed brightness, they match up pretty well at first, but then right after perihelion, the real measurements just peel away from the prediction. The predicted curve drops off smoothly, but the real brightness just runs flat. It's like the comet looked at our predictions and said, yeah, no, I'm going to do my own thing. What this means is that 3I Atlas is still pumping out gas and dust at a rate that's way more consistent with being close to the sun than being on the way out. It's acting like it's still being cooked, even though it's not. Now you might think, okay, maybe there's just some leftover glow, some residual material hanging around in the coma that's taking a while to dissipate. That could explain the brightness staying high, right? Except the images completely contradict that explanation. When the astronomers took the newest deep exposures and stacked them together to bring out faint details, what they saw was not a coma that's just sitting there fading quietly. What they saw was structure, layers, activity. The coma is being actively fed by fresh material. You can actually see multiple shells in the inner part of the coma. These are faint arcs of gas and dust, and they're nested inside each other like tree rings. Each shell represents a pulse of activity, a burst of gas escaping from the nucleus. The outer shells match up with activity pulses we already knew about from earlier observations. But there's an inner shell that's new. It wasn't there in the earlier image stacks, it just showed up. That means at least one new burst of activity happened recently, not weeks ago when the comet was near the sun. Recently, late in the game. When things should be calming down, when the comet should be getting quieter, it instead had another outburst. It threw off another wave of gas and dust. And if you look at the tail, it's telling the same story. Instead of shrinking into this thin, lazy streamer that's just kind of drifting along, the tail is still crisp. It's still defined. In fact, in the latest images, the tail shows this sharper, more defined spine, this bright central line of dust running right down the middle of it. That's exactly what you'd expect from an active jet, from a vent on the nucleus that's still firing, that hasn't switched off yet. So visually, just by looking at it, the comet is telling you very clearly, I'm not done. Now, let's talk about the actual measurements, the numbers behind this alert, because this is where it gets really interesting. The latest estimates of how much gas and dust 3I Atlas is throwing off, the actual production rates, are not doing what they're supposed to do. They're not sliding down a smooth ramp towards zero. They plateau, they level off. And in some wavelength bands, they even bump slightly upward. That's not how a cooling, dying coma behaves. That's not what you see when a comet is winding down. The spectral lines, which are like fingerprints that tell us what gases are present, are still strong, especially the lines from certain more stubborn gases, the ones that take longer to heat up and vaporize. Those are still showing up loud and clear in the data. And the ratio between different gas species has shifted again, which tells us that the chemical makeup of what's coming out of the comet is changing. The inner coma is enriched with fresh dust that wasn't hanging around earlier. That's your first big clue that it's not just the surface material that's been sitting there since perihelion. This is deeper material. Layers that are further down inside the nucleus are still being heated up, still crossing their vaporization temperature, still turning into gas and escaping. But here's the most telling part of today's alert, and this is really cool. It's hidden in something called the orbit solution. Every time new position measurements come in, NASA's teams update the orbital calculations for the comet. They figure out where it's been, where it is now, and where it's going. And to get those calculations really accurate, they have to account for something called non-gravitational forces. See, most objects in space, like asteroids, are basically just rocks. Gravity from the sun and planets is the only thing pushing them around. But comets are different. When a comet is actively venting gas, those jets act like tiny rocket thrusters. The gas shooting out in one direction pushes the nucleus in the opposite direction. It's Newton's third law. And those little pushes add up. They actually change the comet's trajectory in measurable ways. So in the orbital calculations, there are these non-gravitational terms, these extra little accelerations that account for the jets pushing the comet around. And if 3I Atlas were calming down, if the jets were switching off and the activity were dying down, those non-gravitational terms should be shrinking. The comet should start to behave more and more like a dead rock, driven almost entirely by gravity, with less and less push from the jets. That's not what the new calculations show. The magnitude of the non-gravitational acceleration hasn't collapsed. It's holding steady in some directions. It's even a hair stronger than it was a few updates ago. That means the jets are still firing. The comet is still pushing itself around. It's still steering itself with these gas vents weeks after perihelion, when by all rights it should be shutting down. So let's put all of this together. The brightness isn't dropping like it should. The coma is growing new shells. The tail is still sharp and defined. The gas mixture keeps changing and evolving, and the non-gravitational acceleration, the jet activity, has not gone away. That's why NASA called this out. That's why they issued this alert. 3I Atlas is still active, and it really shouldn't be. So what does this actually mean? What's going on inside this thing? Well, to understand that, you have to think about how heat moves through a comet nucleus. It's not like heating up a rock in your oven, where everything warms up evenly at the same time. Comets aren't solid chunks of rock. They're porous, they're layered, they're full of pockets and voids, and they're made of a mixture of ice, frozen gases, dust, and rock, all jumbled together. When the comet was near the sun, the surface got cooked first. The sun's radiation heated up the outer layers, and the ices there started vaporizing. Those outer layers gave us the wild early activity, the big outbursts, the bright flashes, all the dramatic stuff we saw near perihelion. But heat doesn't just stop at the surface. It conducts inward, it migrates down into deeper layers. And this isn't a fast process, it takes time. So right now, even though the comet is farther from the sun and the surface is starting to cool off, there's still this heat wave moving through the interior. It's still reaching pockets of ice that are deeper down, that haven't been touched yet. Some of these ice pockets have been sitting in the dark for billions of years. They've been frozen since this comet formed, possibly in another star system entirely, possibly before our own solar system even existed. And now, for the first time in billions of years, they're getting warm. When those deep pockets finally cross their threshold temperature, when they finally get hot enough to vaporize, they don't care that the comet is technically getting farther from the sun. They don't care that it's supposed to be calming down. They vent anyway. The ice turns to gas. The gas pushes its way up through cracks and fractures in the layers above, and it bursts out at the surface. That's why the activity curve has these bumps in it instead of just a simple, smooth decline. Each bump is a new layer waking up. Each bump is a pocket of ice reaching its vaporization point. And every time that happens, it's not just more of the same gas. It's gas from a different location inside the nucleus, from a pocket that was under different pressure, that has a different chemical composition, that finds a different route to the surface. New fractures open up to release it. Old fractures get widened by the pressure. The balance between different vents shifts around. From the outside, we see the result of all this. We see new shells appearing in the coma. We see new structure showing up in the tail. We see patterns in the brightness that don't match the smooth curve we expected. And we see a non-gravitational acceleration term that refuses to go away. But from the inside, from the comet's perspective, what's happening is actually much simpler. The comet is still changing. It's still evolving. Layers are still waking up. And this is where this alert really matters, because an active comet isn't just bright and interesting to look at. An active comet is under constant stress. When gas is pushing its way through cracks and fractures, that exerts force on the surrounding material. When jets are firing from off-center points on the nucleus, not right at the poles, but from random spots on the surface, that creates torque. It twists the nucleus. And if the comet's rotation is changing because of all this jet activity, that changing spin pulls on weak regions near the surface. It creates stress patterns. We've watched comets in our own solar system follow this exact path. They stay active, they stay active. They keep staying active even when we think they should be calming down. And then one day, they're not a single nucleus anymore. They're a string of fragments. The stress was too much. Something gave way. A fracture propagated all the way through, and the comet broke apart. Right now, there's no confirmed split in Three Eyes Atlas. The inner core still looks like one object in the images. The strange shapes we've seen, the elongated or peanut-like appearances, those could still just be active regions lighting up different parts of the surface. They might not be separate pieces yet. But if this comet stays active this long, at this level of intensity, the risk only grows with every passing day. Every new layer that vents adds more torque to the spin, more internal pressure trying to crack the nucleus open, more thermal stress as different parts heat and cool at different rates. If the activity finally tapers off in the next few updates, if the jets fade smoothly over the next week or two, and everything winds down the way it's supposed to, then this alert is just one more wild chapter in an already incredible story. It'll be the story of a damaged but intact interstellar visitor that survived one brutal pass near our sun and then sailed away to continue its journey through the galaxy. But if the activity keeps hanging on, if more shells keep appearing in the coma, if the tail structure keeps sharpening instead of fading, if that non-gravitational push refuses to drop off the way it should, that we're moving into completely uncharted territory here. We're watching an object from another star system stay alive longer than our models predicted. We're watching it push itself harder than we thought it could on the way out, and nobody knows what that means. Nobody knows how long it can keep this up. Nobody knows if there's some internal structure, some strength to this nucleus that we haven't accounted for, or if we're just watching the slow build-up to something catastrophic. So the real question now isn't just whether 3 Atlas is still active. We know it is. NASA just confirmed it. The real question is how long can it stay this active before something gives? How long can these jets keep firing, these layers keep waking up, this stress keep building before the nucleus can't take it anymore? We're in this really strange position where we're waiting for the next update, the next set of observations, the next alert, not knowing if it's going to say that things are finally calming down or if it's going to tell us that something even more extreme just happened. Maybe we'll see the brightness finally dropping off normally. Maybe we'll see the jets switching off. Or maybe we'll see new features appearing. Maybe that peanut shape will separate into distinct objects. Maybe we'll watch this interstellar visitor fracture in real time. I can tell you right now, I'm checking for updates every single day because this is unprecedented. We've never had an interstellar comet stay active this long after perihelion. We've never had this much detailed data on an object from another star system. We're literally writing the textbook on interstellar comet behavior as this unfolds. And the thing that gets me, the thing I keep coming back to, is that this comet has already survived a journey we can barely comprehend. It formed around another star. Who knows how many billions of years ago? It got kicked out of that system somehow, maybe a gravitational interaction with a giant planet. Maybe its star went through some violent phase, but something threw it into interstellar space, and then it drifted.